We've looked at double slits and many slits. What happens with a single slit? Well, when light strikes a single slit, interference occurs between the individual waves that together make up the wavefront. The light is incident from the left and hits the red line here, which is the single slit, or contains a single slit. Each individual wave that comes out of this spreads out as it passes through the slit and creates the interference pattern that you see below. Here you can see there's a wide central maximum pattern, and then there's a much dimmer secondary maximum located above and another one below. Let's look at single slit interference a bit more. When light hits even a single slit here, we can see that interference is going to occur between the light at the center of the slit and the light at the bottom and at the top. For single slit interference, we can get the distance from the central maximum to the first minimum by using the same equation that we did for the double slit experiment. But in this case, we're going to substitute 1/2 of big D, capital D, which is the size or the diameter of the aperture, or the distance from the top of the slit to its center. So the equation for the minimum m equals 0 becomes x is approximately m plus 1/2 lambda times capital L divided by small d, then substituting 1/2 capital D for the small d, and only looking at the 0th order minimum, we get x is approximately 1/2 lambda L divided by 1/2 capital D. So the distance from the center to the first minimum for a single slit experiment will be x is approximately lambda capital L over capital D. The wavelength times the distance from the slit to the screen divided by the diameter or the height of the slit. Let's have a look at the profile of intensities for the single slit. The resulting pattern of light and dark stripes is still a diffraction pattern. The width of the central maximum is 2 lambda over capital D, and as D gets smaller, as you can tell from that equation, 2 lambda over D, the central maximum must become wider. And as capital D gets larger, the central maximum gets smaller. And again, you can see by looking at the profile that the intensity is very, very strong for the central maximum and then drops off precipitously as we go to higher order maximum. Single slit interference is very important. The width of the central maximum is important for optical instruments, including our eyes, as it limits how clearly we can see. Simply having an aperture, or hole, or slit means that the image of every object projected onto a screen, which could be a film, a sensor, or our eye, will have some spreading and fringes, however slight. The smaller the aperture, the greater the spread, and so the less clear an object, and the more it might overlap with the images of other objects. The less we can resolve one object from another. That's why an eagle's eye is so large, why large lenses on cameras give better pictures, why telescopes have to be large, etc. And as the size of the aperture increases, so does the resolution. Now let's look at diffraction interference around an object. This is just like the bright spot we discussed at the beginning of the unit, where we looked at a light shining on a coin, and inside the shadow we saw a small white spot. The picture on the left illustrates this. Well, light bends around any object, and where the light from all sides constructively interferes, we're going to get a bright spot, and that's what happens in this case.